Good morning, good evening, good afternoon, depending on where you are joining us in the world. Welcome to the MECI Alliance seminar series. I'll be your host for today. My name is Brian Anthony, but it's my great pleasure to introduce Professor Carlos Portela, Professor of Mechanical Engineering, focused on architected materials, learning from nature and pushing the bounds of what humans can do, both looking at additive manufacturing processes and beyond. So his talk today is towards 3D architected materials beyond the laboratory. Carlos, thank you for joining us today, and I'll turn it over to you.
Thank you very much, Brian. Let me start sharing my screen. And okay, there we go. So we can get started. Again, thank you very much for giving me this opportunity to talk to everybody today about three-dimensional architected materials, and particularly how can we take these beyond the laboratory. Thanks to everybody who's joining in from all over. So without further ado, really, let's just get started. And let me start really by defining what I mean by architected materials. And I always like to start with this example of natural materials, such as human bone, which to us feels like a homogeneous material. But when we look at its microstructure, we see that it has this sponge-like geometry, which is what gives bone its high strength and toughness. We've also seen other examples of organisms that have some sort of architecture. And in this case, the sea sponges have a hierarchical architecture. And what do I mean by hierarchical? Well, if we zoom in at different length scales, we can pick out structural features at each of these length scales that each serve a purpose, a mechanical purpose. Now, this concept of architecture really isn't new to us, and it is epitomized by the Eiffel Tower. However, one distinction that I want to make from the beginning is that the Eiffel Tower really isn't an architected material. And what I mean by that is if we pick out one of these struts that makes up one of the legs of the Eiffel Tower, and we say it has some length L, and now we look at the effective diameter of one of these legs and say it has some diameter W, we see that L and W are the same order of magnitude, meaning that doesn't achieve what we call separation of scales. Now, the opposite would be some truly architected material that has some overall length scale W and some intrinsic length scale L, which is significantly smaller than W. And we can try to come up with some examples of broad groups of architected materials made by humans. One example are these stochastic architected materials. Best example here are kitchen sponges. We also have fiber architected materials, and the natural example here is carbon fiber composites. And lastly, this broad group of lattices, which we'll discuss today. And one of these examples that I like to bring up are these honeycomb panels that are used extensively in the aerospace industry. So now that we agree, hopefully, on a definition for architected materials, we have to ask ourselves, why do we even bother with doing this type of research? Why do we bother with architecting materials? And I try to highlight 3 points that I find most convincing. First one, it's kind of obvious. If we architect a material and one of the two phases that we're architecting with is either air or vacuum, we naturally will make materials that are extremely lightweight. You can imagine if we're still trying to put probes in other planets, we want to be able to do so efficiently, meaning that we need materials that are lightweight, but also mechanically robust. The second point that I like to bring up, it has to do a lot with length scale. So in particular, with architecting at the nanoscale, because only then could we really tap into these so-called size effects. What I mean by that is that materials at the nanoscale really will behave differently from what we expect them to behave like in bulk. So a neat example here is these nanolattices made out of hollow tubes of a ceramic, which were demonstrated to, after being deformed to 50% of their original height, they actually recovered and didn't shatter like a typical ceramic would, but instead it behaved more like a rubber. You can imagine if we extrapolate this behavior to larger scales, this really would change the notion of how we think about ceramics altogether. The third point that I want to bring up is this idea that architecture can really help us absorb energy and mitigate impact. This neat example here shows a bistable material, and all that means is that it has two stable configurations. One is the collapsed state, and the other one is the expanded state. And it was shown how going from one of these, the expanded state, to the collapsed state really helps you dissipate some energy, enough such that after dropping an egg on top of this material, you could really prevent this egg from breaking. If we take this concept and start thinking about how we could potentially make car bumpers in some architected form such that after a minor impact, it could actually absorb energy, but we don't need to necessarily replace them, but rather just pop them back into the original configuration. This would really be a game changer and a nice application of architecture. So we can also take a step back and look at architecture materials from a broader engineering perspective. And to do that, I'm going to pull up these, what we call these Ashby plots, where all we're doing is taking all materials that are known to us, such as foams, natural materials, ceramics, metals, and we plot them on the same axes. And in particular, here on the x-axis, we have something like density. On the y-axis, we have some mechanical parameters such as the Young's modulus or the stiffness of these materials. We can do the same with other properties. In particular, here I have strength. And the key takeaway, the reason I'm showing this here is that I hope you notice that there's this significant untapped property space where none of these materials that we currently know and work with can actually get to. But that is exactly where architecture materials could enable us to really tap into. What I mean by that is, so architecture materials, I mentioned they can be very lightweight, but also have very nice mechanical properties. And not only that, I think throughout the talk, you will see how the parameter space for these architecture materials is so broad that the idea of solving the inverse problem, such as picking what properties you want and then designing the architecture in the right way, it really is something that we could start tackling and doing. Now, I've been talking extensively about mechanics, but one point that I want to bring up is that architected materials are not just about mechanics, and there really are multi-physics problems that you could start tackling with architected materials. Just two brief examples are, for instance, an intersection of mechanics and thermal sciences. So these are the ceramic lattices that I mentioned earlier. We know that they're recoverable, but when we look at their thermal properties, we see that they're actually extremely low in conducting, have extremely low thermal conductivity. Another example, and in particular here, is intersecting mechanics with photonics. So these lattices that have pores on the order of hundreds of nanometers, once you apply some mechanical strain, you change the sizes of these pores, and that naturally will change the way these materials interact with light. So this brings us to the roadmap of the problems that I want to discuss with you today. And I'll try to highlight three key hurdles that our field of architecture materials is facing or has been facing for the last few years. One of them is that we need to start thinking about how these materials behave beyond just quasi-static behavior. We want to see how more realistic deformation could be mitigated by these materials. The second point that I want to bring up is kind of we need to retrain our brains into thinking that architecture materials are only for stiff and strong applications. And in particular, we can start thinking maybe at soft applications where architecture really could benefit, could bring us some benefit. And the last point is this mentality that we need to go beyond just fabricating test samples or experimental samples and really be able to fabricate large volumes of these materials. Only then could we start really thinking beyond laboratory settings. Before I jump into these three hurdles that I want to discuss, I want to give a brief overview as to how we fabricate and test these materials. So I'll try to divide the fabrication into two sections. So the micro or nanofabrication process, and this is mainly how we've been doing it in our research, but it's representative of a lot of what the community is doing nowadays. So we can fabricate solid architecture, solid materials, or hollow materials, as I described earlier. And this all revolves around a process called two-photon lithography, which really enables us to print three-dimensional structures with nanoscale resolution. The way this works is that we put a drop of a photoresist on a substrate of choice, and then we can tightly focus a femtosecond laser. And wherever we trace this in 3 dimensions, we're going to solidify or polymerize the material locally. Once we're done tracing the structure that we're interested in fabricating, we can then wash off the photoresist that we did not polymerize. And what we're left with is this polymeric, either nano or microlattice, depending on what features you decided to print. Now, to make these hollow, we start off with this polymeric nano or microlattice as our template. And then we go through a conformal coating process. And in this case, I'm showing atomic layer deposited alumina. So once we go through this process, we have this core shell composite, which has ceramic and polymer, ceramic on the outside, polymer on the inside. And since we're interested in making these materials lightweight and very efficient, that means we have to somehow get rid of the polymer on the inside. So we do this by cutting some sacrificial beams and then putting these materials into some oxygen plasma process that now gets rid of this polymer on the inside. And we're left off with this hollow ceramic architecture. Now at the macro scale, nothing too fancy. Typically this revolves, I mean, this is actually all thanks to advances in additive manufacturing processes. What we've been using in our research extensively are these digital light processing 3D printers. Again, nothing too fancy. The way these work, you have some resin pool and then a projector that gives you a 2D projection of a given layer. And once the print head starts moving in the Z direction, your part starts emerging from this polymeric bath or the resin bath. Okay, so that kind of covers the fabrication very generally. How do we actually test these materials? How do we understand their mechanical properties? Well, at the macro scale, again, nothing fancy. We use universal load frames where we typically put some sample that has some characteristic length scale L. It has some footprint area that we'll define as A. And once we apply some force, we can come up with some measure of the stress that we're applying onto this architected material. And when we deform it by some amount delta, we can then come up with some measure of our engineering strain. And typically these experiments are all quasi-static. And what do we get out of these experiments? Well, what we're looking for is this stress strain curve. And what we extract is just sometimes just a couple of parameters. One of them is the effective stiffness of this material, which we take as the slope of the linear loading regime. And we're also looking as to what kind of measure of strength we have for these materials. So we'll take that to be the onset of nonlinearity in this stress strain curve. So now at the micro scale and nanoscale, this is where things get a little bit more interesting. How do we test these materials? One of the setups that we've been using extensively throughout these years is this scanning electron microscope that actually has a nano indenter inside it. So let me zoom in to give you an idea as to what's going on. So what we're seeing here is the indenter tip. This is the sample holder. We still can't see the sample, so we really have to zoom in further before we can actually appreciate the sizes of the kinds of samples that we can make. And here on the right is just our flat punch. This is what we'll use to compress this material. To give you a sense of scale, if we imagine a human hair falling inside this chamber, this is approximately what it would look like right next to one of our samples that we compress. Okay, with that, let me jump into the first hurdle that I want to discuss, and it's this push to go beyond quasi-statics. What do I mean by that? Well, our comfort zone and really my training ground was in doing these uniaxial compression and tension experiments of a variety of materials. But this all was done very slowly and as I mentioned, just quasi-statically. But we really wanted to push the envelope further, and especially at the micro scale. How can we start studying materials with dynamic deformation at these small scales? So one of the things that we've done is started to look at how waves propagate through these periodic architected materials, particular lattices. And more recently, here with collaborators at MIT, we've been looking at how nanolattices actually respond to much faster stimuli such as supersonic impact. So today I'll be discussing mainly just the wave propagation of these in these materials. So this leads us to the obvious question: why do we want to do this at the micro scale? And the short answer is that we're looking into this very interesting regime of megahertz. That's where our length scale really helps us tackle. And why megahertz? Well, recently we've seen a lot of very interesting developments in the biomedical community that use ultrasound in these frequencies to get really, really good resolution images of tumors, for instance. Another example has been the ability to manipulate individual cells or bacteria inside some fluid medium. And what I'm going to show here in a second, it's a fluid channel that has a bunch of these acoustic bacteria floating in it. And once a standing wave gets created inside this channel, these bacteria will actually be able to be segregated to the antinodes. So here's a video of it taking place. Anything white is bacteria. So a standing wave gets created, and you see how these bacteria will naturally just go to the antinodes of the standing wave. So this is great, but you can imagine a standing wave is quite limiting. So how could we actually have more tunability into how we can segregate or remove these bacteria? And this is where I think architected materials really could help us achieve higher tunability. And one example in our work where we try to tackle this aspect of tunability and how mechanical waves could be tuned throughout a material is actually revolves around electrochemistry to be able to get some tunability. So what do I mean by this? So you can think of this material as a battery. So we go through our typical two-photon lithography process. This material then has some conductive core, some conductive coating applied to it. And then we have an additional silicon layer deposited on the outer side of these beams. Now, when this battery material gets submerged in a lithium-containing electrolyte and some current is flowed through it, we drive this lithiation process where lithium and silicon are actually alloying on top of these beams, and it comes with a significant volumetric expansion, which then leads to these very nice plastic buckling patterns that create this nice reconfiguration. Now, this is actually, think of it again as a material. That means that we can reconfigure it, but we can charge it and discharge it, meaning that we can go back and forth and really get whatever pattern we're really looking for. So this is a video of it actually taking place, which shows us that is actually quite controllable. The other aspect that we can highlight here is that by introducing defects, we could also really control what kinds of domains we can form in a material that reconfigures in this way. And it has tremendous impact in terms of how waves can propagate through these materials. So in order to highlight this point, so what I'm showing here is what we call a dispersion relation. So you could think of it as just a representation of what modes can actually propagate through this material. And here, there's nothing interesting going on, but let me actually show you what would be interesting. So once this material gets fully reconfigured, so fully lithiated, we see the emergence of these green regions, which are called band gaps, meaning that these frequencies cannot propagate through this material. Not only that, so again, let's think again of this material as a battery, meaning that we can charge it and discharge it. And we start seeing that in a discharged state, these band gaps actually shift. So we see not only the emergence of band gaps, but also full tunability of these band gaps. And if you could arrange these different domains in the right pattern, this really could open up possibilities to control the way mechanical waves can propagate at these scales. Okay, with that, going to the second problem that I'd like to discuss, and this idea that we need to think beyond just making stiff and strong materials. So far in our community, we've been looking extensively at these classical architectures that have nodes. And so lattices, for instance, they actually have nodes. We've recently seen a lot of work on nodeless architectures, materials that are just made out of curved shells. But there actually is a medium point that is neither of these extremes, and that's something that we explored, and we arrived at these woven lattices. So something that really isn't nodeless, but it doesn't have a node in the classical sense. So for inspiration, we really started looking at nets, and we see that nets are nice in the sense that they can reconfigure, and they're made out of many of these interesting fibers. So we can take one of these fibers and we can weave these fibers to make an effective beam in our classical lattices. So we can come up with some effective beam radius, some effective length, some fiber radius. And the remarkable thing, again, this is where the nodes come in. So at these junctions of these effective beams, we don't have a monolithic chunk of a material, but instead we have some very nice entanglement of all these fibers. So once we came up with this concept, so we started off with our classical monolithic lattice materials, which they can be very easily represented by the geometry and also just by the effective relative density. So which is nothing more than a fill fraction. This is what I'm showing here, which you could represent it just as a function of the radius to length ratio. So the slenderness of each of these struts. Once we go into the woven regime, we see that we add many more knobs to really control the mechanical properties. Such as the fiber radius, the effective beam radius that I'm showing here, the length of the struts, and even the pitch of these helices that we're weaving together to make these materials. So again, how do we make these? We go through a 2-photon lithography process. The nice thing is that this, besides the resolution, this process allows us to print these complicated structures without ever needing some support structures. And we can then readily fabricate larger tessellations, such as 4x4x4 tessellations of these woven materials. And this are actual micrographs of what these samples look like. The remarkable thing, as you can see, so these are actual fibers that are not fused together. There really is a separation of a couple hundred nanometers that really enables us to really capture the woven mechanics that we set out to explore. So let me show you a nice video of the comparison between something that is woven and not woven in the same geometry, same amount of material. And when we started seeing, so when we start doing these tension experiments, we see that these materials really do behave like nets. They have this very nice realignment, and they elongate a lot without having this kind of catastrophic failure that we observed with the materials on the right. And then when we go into compression, we again see very nice reconfigurations, of course, way more compliant than the other materials. But the remarkable thing is that we're not accumulating permanent deformation. And once we do the unloading on the sample on the right, you see that all of this material really is not what you started with. It's permanently deformed, and you really can't use it again. In contrast, our woven materials really do show this very nice resilience after large strain deformation. So where can we take these beyond the lab? Well, we've seen that the flexible electronics field is quite interested in making materials that could extend extensively. And currently, the way this is achieved or mitigated in a sense is by having these ribbons that are either buckled or curved, and then as you stretch them, they straighten out a little bit. But once you really stretch them, chances are you'll have some permanent deformation that could really compromise how your flexible electronics perform. Also, we've seen a push to try to get some sort of three-dimensionality and with these kinds of ribbons. And the nice thing is that thinking of these woven architectures can really help us try to tackle these ideas. We can make materials that potentially could be conductive, that could extend a lot, way more than what's typical for flexible electronics. And because of the way we design them, we get this three-dimensionality for free. The last point that I want to discuss, and this is one of the most crucial ones, is thinking beyond the idea that we're just making test samples for a laboratory, but really trying to scale up these materials. And for that, I'm going to bring back this slide when we were talking about nodes or nodeless materials. And before I try to draw some comparisons between these two, but these materials also have a couple things in common. In particular, they all rely on symmetry, and periodicity to achieve these nice mechanical properties. And also they rely on additive manufacturing processes to be able to be made. Why is this somewhat problematic? Well, despite all these advancements in additive manufacturing processes, we have inherent defects that at small scales can get amplified. And in particular, they make these assumptions of symmetry and periodicity really go out the window. And the other aspect is that some additive manufacturing processes either are too expensive to really fabricate large volumes of these materials, or just are impossible to really scale up. So based on these constraints, we started thinking about possibility of making architected materials and in a way that we could bypass advanced additive manufacturing processes. And for inspiration, we started looking at these block copolymers, which we know at the nanoscale, depending on the fill fraction, could really give us some very nice and interesting morphologies just by tweaking how much of each copolymer you put in. We've seen at the microscale also these nanoporous foams that naturally just form very interesting patterns. And at a larger scale, these so-called bigels give us pores now on the order of hundreds of microns. So what we set out to do is find some material that really could give us these very interesting patterns at the microscale, but also could give us some sort of tunability, such as what we're seeing at the nanometer scale with block copolymers. So what did we eventually arrive at? So we started playing with these polymeric emulsions that would undergo phase separation upon polymerization, to the point that if you do this right, you could have bicontinuous morphologies form when you finish this polymerization. Why is bicontinuity something that's important? Well, that means that once you're done polymerizing these materials, these emulsions, you could really get rid of one of the two phases, which leaves us with a porous template. And what's remarkable about this process is that in a matter of hours, we could then fabricate cubic centimeters of these materials. And if we look at one of these cross sections, we see that indeed it's nicely porous. We could get rid of one of the two phases, and we have our pore sizes on the order of about 10 microns. But again, we're interested in making these materials lightweight and efficient. So what was the next step? Well, we coated them conformally using atomic layer deposited alumina again. And we wanted to get rid of the polymer on the inside. So we put them through an oxygen plasma process. And the result was really these large chunks of ceramic material that was about 99% air, but really had this nicely smooth and also doubly curved nanoscale shells that we really got for free. Again, no additive manufacturing went into making these materials. So the next step for us, we're interested in the mechanics, was to make some prototypes and try to understand what parameter space these processes could actually enable us to achieve. And I'll just kind of give you a brief taste of what we found. So we were able to look at different morphologies by picking some preferential directions in the way these polymeric, sorry about that, in the way these polymeric emulsions formed. So I want you to keep an eye on these yellow vectors, which are preferential directions. So this particular set of directions gave us our columnar architectures. When we picked more orthogonal directions, we got what we call a cubic architecture. By just picking two vectors, we got this lamellar architecture. Now we picked non-orthogonal directions, gave us this very interesting trigonal architecture. But we could also do this without picking preferential directions, just letting the process separate on its own. And then we obtain these, what I'll call the isotropic architecture. So once we could compute and get accurate 3D models of these different morphologies, we ran this through a set of finite element simulations, some homogenization scheme that then allowed us to extract the Young's modulus in all directions for a given material that has this morphology. And we can represent them as these colorful surfaces. So this colorful surface here is the representation of the Young's modulus of this material in all directions. And we compared it to two things. One was the theoretical upper bound, which is this golden sphere, which I'm showing here. And the other thing was the elastic surface, or the Young's modulus in all directions of an equally dense lattice architecture. And right off the bat, we started seeing that these materials that are self-assembled could indeed be much more efficient and stiffer than these benchmark lattice architectures. When we looked at the different ones, it really just showcased the versatility of this process. So the cubic one showed us, preferential orthogonal stiffness directions. The lamellar one showed us extreme anisotropy that's ever desired. So very compliant in one direction and very stiff in the other. The trigonal one really showed us that whatever elastic surface you could have in mind, you could pick the preferential directions to really achieve it. But the last point that we discovered, and which was maybe the most interesting one, was when we looked at this isotropic one, and we tried to look for the elastic surface of the octet, or the lattice structure that I've been talking about, we saw that it is actually embedded inside of the elastic surface of this self-assembled structure. And what does that mean? That means that this self-assembled material that never needed an additive manufacturing process could be indeed stiffer in all directions than a more carefully designed and produced lattice architecture. So without further ado, let me show you the experiments and the nice experiments that we performed on these samples. So what I'm about to show here are this self-assemble or these geometries that could be self-assembled with very thin shells. So this is about upwards of 99% air. The walls are just 11 nanometers thick. And when we start compressing these ceramic materials, again, we're surprised by seeing that none of this shatters, but instead these ceramics actually buckle and wrinkle. Not only that, as we continue compressing them, we see that these cycles are quite self-similar and comparable to the initial one, which to us, it means that there's minimal degradation going on, and it's orders of magnitude better than what we've seen for other materials such as nanolattices. So what could we extract and how could we quantify these experiments that I showed you earlier? Well, we could take these individual stress strain cycles, and in particular, we're interested in how much energy can get dissipated by a single cycle. So we can integrate the area inside this curve, and we can then represent that by normalizing subsequent cycles by the initial one. And when we compare it to side-by-side experiments of lattices under the same kind of stimulus, same amount of mass, we saw that these materials, the self-assembled materials, are actually much more resilient, in the sense that after 10 cycles of extreme deformation, we retained about 40% of the energy absorption. And we see the same trend taking place for the stiffness and also the strength, which led us to the question, why is this happening? This seems a little bit counterintuitive. Well, the answer to that question really lies behind the geometry. So what I'm showing here is a probability distribution of finding a given curvature inside of this material. And what we see for the self-assembled materials is that this is a single peak in this distribution that is actually very close to zero. So very small curvatures, and they're all localized about some mean value. In contrast, if we look at one of these lattices, we see that we necessarily have one distribution around here where one of the curvatures is zero. We're looking at a cylindrical tube. And then even when we add fillets, and we're adding fillets at these nodes, because otherwise these sharp corners will have negative infinity curvature, we see that these distributions for lattices are necessarily bimodal. There is no longer just one peak. And also the absolute value of these curvatures is much higher than what we're seeing for our self-assembled materials. What does that mean from a mechanical standpoint? Well, when we look at our simulations, we can start seeing that stress concentration actually takes place where there is high curvatures. And this really supports what we've seen in experiments that lattices start fracturing at these nodes. Okay, with that, it leads us to the end, and I don't want to be repetitive, so I'll just briefly summarize each of these hurdles that we discussed. So one of the things that we've been stuck with is just looking at the behavior of these materials quasi-statically, but if we want to take these outside of the lab and really use them in real applications, we need to look at more realistic dynamic loading. and that's something that we're hoping to contribute to over the next few years. We also need to retrain our brains into just thinking that architected materials are good for stiff and strong applications. Actually, there's a lot of tissue engineering applications or also flexible electronic applications that really could use some sort of three-dimensional architected materials that are very compliant. And lastly, I think this is the most important hurdle that as a community we have to overcome. And it's this issue of how do we scale up the fabrication of nanomaterials? And we're seeing that self-assembly processes could lead the way. We still need to do a significant amount of work to really control the way we or the morphologies that we get with these self-assembly processes. But again, this is the most interesting challenge that we have yet to overcome as a community. Very briefly, I just really want to thank everybody who has made the research that I just showed possible, in particular the Kochman group and the Greer group at Caltech, my collaborators here at ISN, at MIT, ARL, UCLA, and ONR for funding this work that I've just presented. And with that, Brian, I'll be happy to answer any questions or comments that you might have.
Carlos, first of all, I send you the virtual and the physical clapping here. So nicely presented and very interesting work. Participants, please enter your questions in the Q&A, or you feel free to chat me directly. But Carlos, let me ask a sort of a lead-off question here. I guess I'm just contemplating maybe it's the intersection between beyond quasi-statics and test samples. Have you thought at all about after you have these large materials that have been constructed in a way other than additively, how do you machine them? How do you cut them? What are the questions that if you want them to respond to dynamics in a particular way, is that undercutting your ability to then form them or cut them or trim them, or what are the machining aspects that might come up, I guess?
That's a great question. That's something that we've actually started to try to address because for the first time we now have a nanomaterial that we can hold in our hands. One of the challenges has been, controllably machining pieces for a given application. And one way that we've thought of doing this is using something like focused ion beam. It really is just like mechanically cutting, but in a very controlled way. I think the best answer I can give you is that I haven't tackled those issues yet because we're just entering that process of having materials that we need to machine.
Very good, but challenges down the road, certainly, and very interesting research questions that'll come out of that. We have some questions in the Q&A. Let me pose the first one. Do you see a distinction between what you're calling architectured materials and metamaterials?
It's a great question. I'd say it's a matter of choice. I think I could have interchangeably said that these are all mechanical metamaterials. I tend to reserve the term metamaterials when I'm really talking about some other physics beyond mechanics. So in particular, photonic metamaterials or yeah, I think that's the short answer is I think it's by choice. I tend to refer to these as just architected materials unless I'm really going into these multi-physics domains.
Very good, thank you. Another question here. What kind of provision is there for this type of architected material before tension loads? The parenthetical, are they only able to withstand compression loads?
So that's a great question. And I mean, the answer is no, that they can withstand tension, but there's been very few explorations in tension at these scales. And the reason why that's the case is it's very hard to do these tension experiments at such small scales. I think, so the video that I showed of us pulling this woven material, it really is kind of, we had to invent a way to do this. So to give you a sense of why it's challenging, so it's no longer just easy to do it with a flat punch, and then you need to be able to grip onto this, and to be able to grip properly, now you're having to move this tip with micron precision to be able to to lodge the grip and then really pull on it. So yes, there's a lot to be done in tension in particular. It's not impossible. It's just that it's a little bit more challenging than just doing compression.
Very good, thank you. There's a question that was chatted to me directly, asking, I think, roughly about the applications of the sort of moving beyond the test sample, and where do you see as the first opportunity, and maybe the most exciting opportunity in the use of such materials in either designed or vehicles, what have you?
So one of the applications that has been explored quite extensively in tissue engineering is having these materials serve as scaffolds for the growth of cells. And I think there's been quite some work recently on stem cell differentiation based on the stiffness of a given architecture. So this is something that I think these materials could readily contribute to. So if you could architect a given structural stiffness, and that a stem cell will differentiate either way depending on how stiff or how compliant that material is. I think that's a field that we could readily try to contribute to. We've seen some applications also because of the high surface area of these materials and energetic applications. So thinking of nano batteries, energy storage applications are definitely a possibility. And one of the things that we've been exploring, I mentioned in passing, the supersonic impact. So we want to be able to fabricate resilient coatings such that, for instance, micrometeoroids really would not be able to penetrate them, or at least that they would mitigate a lot of that energy. So I think I would summarize those few applications as potentially readily problems that we could readily tackle pretty soon.
Very nice, thank you. Quite a diverse collection as well. We'll take one more question here. This is also texted to me directly from a doctoral student. Interested in the beyond test sample section. They want to know, can you make graded architectural materials in a controlled manner? And I presume that means sort of varying the profile of the material, the aggregate property, as a function of space throughout the material.
That's a great question, and that's something that we are trying to address. I think it could be possible by having some sort of functional grading in the stimulus, that either through chemistry, through thermal processes. You can imagine how beneficial it could be if you have some part of this slab that we self-assembled be isotropic, and the other one be quite stiff in a given direction, such that it could prevent some tear forming in that area. It's doable. It's just very hard to control, and that's something that we're looking into actively in our group.
Okay, very nice. So we as I alluded to, letting the people that was going to be the last question, we got two more in. So let's see if we can get a couple more in, if you're okay with time. Deepak asks, can you briefly tell us the status and challenges to exploit bistability or multi-stability at the micro and nanoscale?
That's a great question. So we've seen some works that can indeed harness bistability at these small scales to absorb impact, for instance. Issues that can come in the process of studying these problems. For instance, you can imagine you make a material, you compress it, you see nice bistability. To be able to reuse this material, you need to be able to also controllably pop it back into the original configuration. So you can do this mechanically. It's complicated, but it kind of defeats the purpose if every time you use it, you kind of have to go in and pop it back into the original configuration. That's one of the challenges, just testing this and going beyond just a proof of concept. The other issue, well, in the sense, I think at the nanoscale, it might become a little bit easier in the sense that you can get away with what I'll call these structural size effects, meaning that you could have traditionally stiff and brittle materials such as silicon or ceramics actually be able to show some sort of bistability and large curvatures in nano-sized beams before even breaking. So in that sense, I think it's not a challenge. It's the opposite of what you asked. So it's definitely something that's worth exploring. But we haven't done much work in that area.
So I think the next question is somewhat related. Let me paraphrase it. And when looking at the architectured materials, how feasible is the prospect of biomimicry, or more broadly, what are the hierarchies of structures at different length scales that are possible without considering the effects of physical chemistry on the functionality?
Okay, so I will try to answer that question, assuming that we can, in a sense, cheat and use nice additive manufacturing processes such as two-photon lithography. And in that sense, limitations are very few. You know, as I mentioned, like that tool really allows us to have hundreds of nanometer resolution and be able to, now with the recent tool that we got here at MIT, we can now fabricate sample sizes on the order of up to 8 millimeters. So it really depends how long you want to spend making a sample like this, but in terms of length scales, that really isn't a big issue. Maybe one limitation could be the kinds of materials that you can work with. So currently most of the resists that we can use are polymers, and you know, functionality can be limiting. So if you want you know, metals or something like that, then that's a whole separate issue that maybe you could run into later on.
Very good. Carlos, thank you for the wonderful work, the great Q&A participants, and looking very much forward to hearing updates and your progress as you proceed.
Thank you.
So as we are nearing the close of the hour here, folks, I invite you to come back next week, same time, same channel. We're here from Dr. Xia on versatile, high-speed and large-range atomic force microscope design for advanced imaging. And if you have recommendations, either yourself or your colleagues or others, this is our opportunity to engage with our students, our faculty, and external partners. So please do drop us a line. Let us know feedback on the seminar and people that you would like to hear from. And we look forward to your continued participation and questions. So with that, Carlos, Professor Portela, thank you again. And everybody stay safe and have a good remainder of your day.
Thanks so much. It was a really great talk. Have a good day.
Thank you. Bye-bye.